The binomial probability density function is without question more valuable than the hypergeometric, which we just met. Because the binomial probability density function calculates probabilities for a huge class of activities, we will be using this binomial throughout the rest of this course. Indeed, just the name tells us how important this distribution is. The name binomial comes from the root word binary, meaning one or the other, or of two. Think bicycle. The possible answers to a true-false test are considered binary because either one or the other must be selected, yes or no. The video you are watching is possible only because of the binary world we now live in. That was created by a binary computer code, what the word digital really means. Less technically, there are many experiments that have binary outcomes that are of interest to us. What percentage of people will vote yes on the new bond issue? What percentage of people are classified as elderly or classified as susceptible to a new flu strain, or will retire this year, or marry, or divorce, and on and on. Whenever we have two categories, we are looking at a binary random variable. But while we may have many interesting examples of binary random variables, let us stick with the boring coin flipping example to explain the formula. Here is the formula for the binomial probability density function, where P of x equal x is the probability of x successes in n trials, and the probability of a success in any one trial is P. Therefore, the probability of a failure is Q, which is equal to 1 minus P. We can see now why the combinatorial formula is also called the binomial coefficient, because it reappears here again in the binomial probability function. Like the hypergeometric distribution and all others, there are very specific situations in which we can use the binomial distribution. The requirements of the experiment to use the binomial are: 1. The outcomes must be binary, meaning there can only be two possible outcomes, one thing or the other. This is often described as being either a success or a failure. If the random variable is the number of heads, then getting a head is a success, and getting a tail is a failure. Number 2, the probability of a success in any one trial must be the same from trial to trial, or in other words, the outcomes of each trial must be independent. Flipping a coin is a binomial process because the probability of getting a head in one flip does not depend upon what has happened in previous flips and will have no effect on what happens in future flips. Number 3, the random variable must be discrete, meaning measured in whole numbers. Just like a set of data, a probability density function has a mean and a standard deviation. For the binomial distribution, these are given by the formulas mu equals np. And the standard deviation is sigma is the square root of npq, where n is the number of trials, or flips if we're dealing with coins. P is the probability of success in any one trial, say 1/2 in flipping coins. And Q is the probability of getting a tail, which is 1/2. Also notice that the mean is NP. This is intuitively sensible. What number of heads would you expect if you flipped 100 coins? 50 heads seems to be about right, or half of them. In probability theory, under certain circumstances, one probability distribution can be used to approximate another. We say that one is the limiting distribution of the other. If a small number is to be drawn from a large population, even if there is no replacement, we can still use the binomial, even though this is not a binomial process. If there is no replacement, it violates the independence rule of the binomial. Nevertheless, we can use the binomial to approximate a probability that is really a hypergeometric distribution if we are drawing fewer than 10% of the population. That is, a small n in the formula is less than 10% of capital N. This allows the use of the binomial to estimate a hypergeometric distribution. An example is sampling products as they move along an assembly line. This is a hypergeometric problem because we presume that the objects are taken for sampling and would not be returned. That is, they are chosen without replacement. The binomial assumes, in essence, that we are sampling with replacement. This ability to use one probability distribution to estimate others will become very valuable to us later.